Artist's illustration of two merging neutron stars. The rippling space-time grid represents gravitational waves emitted from the collision, while the narrow beams are the jets of gamma rays that shoot out just seconds after the gravitational waves detected as a gamma ray burst by astronomers. Image credit NSF LIGO Sonoma State University A. Simone. On August 17, after a journey taking 130 million years, the gravitational wave signal of two neutron stars, spiraling inwards in the final stages of a merger, finally arrived at Earth. As the surfaces of the two stars collided, the signal abruptly ended, and then there was nothing. Although these stellar corpses, perhaps only 20 kilometers in diameter, were moving at some 30% the speed of light, we saw nothing in the immediate aftermath. Only 1.7 seconds later did the first signal arrive, light in the form of gamma rays. Why did this delay happen? It's an incredible question, and what Joel Mills wants to know. Please discuss significance of the 1.7 sec difference in arrival time between GW and gamma ray burst for the recent neutron star event. Let's take a look at what we saw, and try to figure out why this delay existed at all. Neutron stars, when they merge, can exhibit gravitational wave and electromagnetic signals almost simultaneously. But the details of the merger are quite puzzling, as the theoretical models don't quite match what we've observed. Image credit Dana Barry Skyworks Digital, Inc. As the neutron stars spiraled and merged, the gravitational wave signal got stronger and stronger. Unlike with merging black holes, there is no event horizon and no singularity at the core. For neutron stars, there's a hard surface made mostly of neutrons, 90% with other atomic nuclei and a few electrons at the edge. When those two surfaces collide with one another, it's anticipated that a severe, runaway nuclear reaction occurs, resulting in the expulsion of a significant amount of matter, many times the mass of Jupiter, the formation of a central collapsed object, likely a black hole after no more than a few hundred milliseconds for these particular masses, and then the acceleration and ejection of material surrounding the merging objects. We knew that when two neutron stars merge, as simulated here, they create gamma-ray burst jets, as well as other electromagnetic phenomena. But why the gamma-ray burst occurred 1.7 seconds after the gravitational merger of the neutron stars doesn't have a definitive answer, yet. Image credit NASA Albert Einstein Institute Seuss Institute Berlin M. Kopitz and L. Rizzola. We now know, thanks to observations collected from over 70 telescopes and satellites, from gamma rays all the way down to radio wavelengths, that this is where the majority of the heaviest elements in the periodic table come from. We know that a rapidly rotating neutron star likely formed at the core for a fraction of a second, then collapsed into a black hole. And we know that the first electromagnetic signal from this merger, the high-energy gamma rays, arrived just 1.7 seconds after the gravitational wave signals came to an end. Over a time scale of those 130 million years that the light travels, this means the gravitational wave and electromagnetic signals traveled at the same speed to better than 1 part in a quadrillion 1*10^15. In the final moments of merging, two neutron stars don't merely emit gravitational waves, but a catastrophic explosion that echoes across the electromagnetic spectrum. The arrival time difference between light and gravitational waves enables us to learn a lot about the universe. Image credit University of Warwick Mark Garlick. But why did the gamma rays get here afterwards? Why didn't they simply arrive at the same time as the gravitational waves? There are two possible likely scenarios. The gamma rays weren't emitted until 1.7 seconds after the first contact of the neutron star surfaces. Or the gamma rays were emitted almost immediately, and were delayed as they passed through the surrounding matter. These two possibilities both contain the caveat that the true answer could be a combination of both factors or an unlikely alternative involving exotic physics like a slightly different speed for gravitational waves and electromagnetic waves. Let's examine how both scenarios could play out. During an in-spiral and merger of two neutron stars, a tremendous amount of energy should be released, along with heavy elements, gravitational waves, and an electromagnetic signal, as illustrated here. Image credit NASA JPL, delayed emission of gamma rays. When two neutron stars collide, we know they generate gamma rays. It's long been the leading theory, for over 20 years, that the origin of short gamma rays bursts is with colliding neutron stars, a picture that's been spectacularly confirmed by the GW 170817 event. But are gamma rays generated on the surface of the neutron stars, from the collision of ejected material with the surrounding matter, or within the cores of neutron stars? If it's either of the latter two options, these gamma rays ought to be delayed. It takes time for neutron stars to merge, to eject material, to have that material collide with the surrounding matter, and then for that highly energetic material to emit gamma rays. If the material is a significant distance away from the neutron star, like tens or hundreds of thousands of kilometers away, that would very simply explain the delay. Alternately, if the gamma rays are generated not on the surface, but in the interiors of the colliding neutron stars, we'd expect there would be a delay as the light took time to propagate to the neutron star's surface, where it could then be released. Gravitational waves aren't delayed by having to travel through dense matter, but light is. This would be extremely analogous to what we observed during the supernova we saw in 1987, where the neutrinos, which aren't delayed by passing through matter, arrived 4 hours before the first light signals did, owing to the fact that the light was slowed by its need to pass through a large amount of matter. Either one of these explanations could cause a delay in the emission of gamma rays. Illustration of a fast gamma ray burst, long thought to occur from the merger of neutron stars. The gas-rich environment surrounding them could delay the arrival of the signal. Image credit ESO, immediate emission, but delayed arrival of gamma rays. This is the other major scenario. Even if gamma rays are emitted immediately, they still need to pass through the matter-rich environment surrounding the neutron star. It's got to be matter-rich, because with neutron stars moving that quickly close to the speed of light through space, and with the intense magnetic fields they produce, material is bound to be ejected and stripped off as they inspiral and merge. This dance has been going on for a long time, and so there's definitely large amounts of matter the light needs to travel through before it can arrive at our eyes. Is there enough matter there to cause that 1.7-second delay? There could be, and that's the other major option. The Vela pulsar, like all pulsars, is an example of a neutron star corpse. The gas and matter surrounding it is quite common, and around the neutron stars seen in GW 170817 might be responsible for the delay. Image credit NASACXEPSUG, Pavlov et al. The way we'll arrive at the answer involves a combination of examining more events in a variety of mass ranges below a combined mass of 2.5 solar masses, where you should get a stable neutron star, between 2.5 and 3 solar masses like the event we saw, where you get a temporary neutron star that becomes a black hole, and above 3 solar masses where you go directly to a black hole, and measuring the light signals. We'll also learn more by catching the inspiral phase faster, and being able to point towards the anticipated source in advance of the merger. As LIGO and other gravitational wave detectors both come and get more sensitive, we'll get better and better at this. The remnant of supernova 19878, located in the Large Magellanic Cloud some 165,000 light-years away. The fact that neutrinos arrived hours before the first light signal taught us more about the duration it takes light to propagate through the star's layers of a supernova than it did about the speed neutrinos travel at, which was indistinguishable from the speed of light. Image credit Noel Carboni. The ESAESONASA Photoshop fits Liberator. Exotic ideas, like a different speed for gravity and light, are completely unnecessary to explain this observation. Multiple different lines of thought involving conventional physics could be successful at describing why a small, 1.7-second delay occurred. While gravitational waves simply pass through matter unperturbed, light interacts with it electromagnetically, and that could make all the difference in the world. Unlike supernovae, however, the object's neutron stars that give rise to gamma-ray bursts are tiny, and so wherever the solution lies, it will likely involve understanding a cataclysmic event on extremely short timescales. While theorists race to catch up, the data is already here. The next event could make all the difference in the world.